All right, so yeah, welcome back. And what we're gonna cover today and maybe in the next 3 lectures is chapter 11, which is about regression. So whatever you do with machine learning, I think you will meet 2 typical problems that you will encounter are classification problems that have discussed so far, and then the other kind of problem is a regression problem. So we're gonna study about what regression problems are, and then we will study a little bit on the learning theory, which we can use for specific kind of regression problems, which we call bounded regression problems. And then we will look at few algorithms that are designed to solve these regression problems. Okay. But here's some motivation or overview. High-level picture. So when you perhaps, if you heard about regression problem, the way you are introduced about the regression problem, it's very likely that, the regression problem is nothing but, what is regression problem? So if you ask this question, the answer that you perhaps got is going to be something like this. Is to find a good function f that goes from the input space to maybe to the output space in a situation where the y is a set of real numbers. It's a subset of real numbers. Okay, and then maybe the way you are introduced about the difference between regression problem and classification problem is that for the classification problem, the target space or output space y is not the real number, it's just something discrete like 0 and 1 or some discrete set. And that is what's happening in classification. And then maybe, that's how I was introduced into the regression. So, okay, the key difference is, in one case, the output space is a subset of real. The other case is just, the finite set. Like, it can be some natural numbers, but it's a discrete set. It's something like 0, 1, or at least subset of integers. Okay, but textbook actually give a much better explanations about what regression problem is. So, this I think is more like superficial difference between regression and classification. And the more crucial difference, which is explained in the textbook, is that, so I would say, it's a bit superficial. Textbook say something more crucial difference between the regression and classification. The key difference is between regression and classification. This is that in the case of regression, the output space has more structure. And the case of a classification is why, in some sense, we assume that y may have some structure, but the problem formulation and the algorithms do not really try to exploit the structure. So what do you mean by structure in this case? What I mean by structure is that, it's a structure, but in the other case, it doesn't have a structure. Try. I want to move this, but okay. So then what do you mean by structure? The structure, by structure, we mean, in this specific case, a distance. So in the case of classification, we can say one output is the same as the other output, but we cannot really say how close these two outputs are. Of course, Connor and so on, we've studied about it, but they are talking about similarity between inputs. As far as the output is concerned, it doesn't say anything about how to compare two different outputs. So they are just different, same or different. That's the only kind of comparison that we consider in the classification case. In the regression case, the story is different. We have a distance. So, how does it make a difference in the actual design of the algorithm? That the key, this difference, existence of a distance, actually make a huge difference between on the design of the algorithm, which you can see, we're going to talk about it a bit more. You can see in the definition of a risk or error. So all these algorithms like a regression and the classification, they try to minimize, find generalization error. So which is not a sample error or empirical error, but generalization error. So if you have a hypothesis H, we cannot compute, but in one way or another, we want to find H which have a small generalization error, okay? But in the case of classification, this generalization error was defined like it's an expectation over X and Y, where if the hypothesis and then intended output are different, we get a penalty. It doesn't really matter. This hypothesis is very much like Y. As long as they are different, they all get the penalty. However, so that's what happens in the classification. But for regression, this risk, we use different risk or different error. The error is defined like this, say for X and Y. So we have a distance D, so we compute the distance between H of X and Y. So this, by this can be distance square, or by distance, I don't mean the exact metric in the sense of metric space. It's something derived from metric, but it's just something which is a bit like measuring the distance between the two elements. So one example can be something like H of X minus Y squared. So then what can happen? One thing that can happen is that suppose we have an example X and Y, and suppose we have two hypotheses, H and H prime. Given X, we have to produce Y, okay? But for H and H prime, what we have is, in both cases, H of X is not equal to Y, H prime of X is not equal to Y. If that is the case, in the case of classification, we say they are equally bad. Bad with respect to X and Y. However, for the regression, so this is the story from the classification. But for regression, the story can be different. If H of X, even when they are different, if H of X is closer to Y, maybe in terms of square distance, then we say that H is better than H prime. So with respect to this specific example, x comma y. So that's the situation in the regression. So you can see the difference. I mean, for the classification, outputs are essentially the output space have no structure. The measure of success all comes from whether we produce exact the outputs, exact intended output or not. That's reflected in this. That's reflected in this. The notion of generalization error there, where in a sense the loss we are using is like indicator functions, which just check whether H produce exact output Y or not. However, for the regression case, so we are being a bit more flexible. So instead of asking the algorithms, instead of looking for a hypothesis that produce exact outputs, intended output, we want a hypothesis that produce an output that is close to the intended target. So we use a difference, like the measure like a different distance here. Okay. So that makes a huge difference between the design of the regression algorithm and the design of the classification algorithm. In some sense, because the measure of success for the regression is more flexible. I mean, even when we don't produce exact output, if we produce something close, then I mean, we are good. I mean, the hypothesis, such an hypothesis is regarded as a good hypothesis. So the regressions allows us to come up with some different algorithm, which can also kind of exploit some the continuous structures in the target space, like a set of real. Okay. So I mean, textbook explain it this way, and I found this is more convincing explanation about difference between regression and classification. So we're gonna study about the regression, and then we will develop some learning theory for the regression, and then also study the algorithms designed for regression. But many tools that you learn for classification will appear throughout our study. So let's look at the definition of regression. Regression problem. Try to define it almost formally. So what this problem assumes, and then what this problem try to achieve, and so on. Okay. So the typical setup of the regression problem goes like this. It's very similar as the one we studied before. We say we have an input space. And we also have an output space Y. Typically, output space Y is a subset of real. I mean, it's a subset of real numbers, but it can be more structured. So although I haven't checked many of the ideas from the research on the regression can be applied if Y is just a metric space, where we can talk about distance. I mean, for a set of reals, we can talk about distance by saying distance between Y and Y prime is just absolute value of their difference. Okay, so that's the typical setup. And I mean, having this metric or distance, that's what makes us shoot all the difference in the regression problem. And then what we assume is that we have a hypothesis set H. So choosing a right hypothesis set is is a part of designing an algorithm for solving regression problems. But the hypothesis set is usually a set of functions that takes X and map it to Y. And then, I mean, what I'm saying now makes sense to some of you, but it doesn't make sense to some others, but doesn't really matter. F has to be measurable so that we can talk about probability and so on. I mean, this is typically true. I mean, in most of the applications or most of the things that you will do. Okay, so Then we have our target. Target is modeled by the distribution. So it's a stochastic scenario. So we have a probability distribution on x and y. The pair x comma y, and then that describes what kind of output we should produce. And then the learning problem is formulated like this. Our input is, as usual, it's a sample which is an independent draw. The examples drawn independently from M. So S is written as x1, y1 to xm, ym. But now the objective is different. So here comes all the difference. So to define the objective of learning, we define a loss function. Okay. And the loss function L, it's a binary function that take two y's and return non-negative integers and non-negative real numbers. And then typical example, this loss function is typically defined by using this distance. Okay, the loss function. So it uses structure that exists in the set of reals. And so, for instance, one notion of the loss is going to be a square loss. That takes take the difference and then the square. And then another example is more generally, we can have an LP loss, right? Where we take the difference between y and y prime. And then take the p's power, okay, where p is typically greater than or equal to 1. Okay. So they are the examples. So you can see that the definition of loss, which forms which is used to formalize what we're gonna want to achieve through the learning, actually exploit this idea of the distance. It's not an indicator, just comparing with the two y's. It is just, it has a much more information here. And then the ultimate goal of learning is to minimize. So using S, find some hypothesis H such that the following is small, okay, or maybe this is better. H, the ultimate goal is H is something that minimizes this among all the hypotheses. What they try to minimize is what we're gonna write R of H, where R of H is defined in terms of loss. So in expectations, expected loss. L of H of X, so if we use the first example, if we use this example, this means that we want to find H that minimize the mean squared error. So this L of HXY is going to be the mean square of the difference between H of X and Y. So it's a mean squared error. So we find something that minimizes mean squared error, where the average mean squared error with respect to this, our target distribution D. And we may use something different, like a P is equal to 1 or P is equal to 3 and so on, that have a similar idea. If H is close to Y, we regard that such a H good. But how much we're gonna penalize the deviation of H of X from Y is determined by choosing different P. And then in that setup, what algorithm can use. So this is some important concept that we were gonna use repeatedly. So this R will correspond to when we talk about regression, we talk about the loss, generalization error, risk, and so on. So this R of H correspond to, in the context of classification, this corresponds to risk, or error, generalization error. And so on. And then sometimes, it's just called the loss. So they were the kind of ultimate objective that we want to minimize in the context of classification. R replaces that objective. Then when the algorithm actually do try to learn a hypothesis from a sample, then what it can use is the empirical version of this R, so which can be read as empirical error or empirical loss. So the algorithm try to achieve this goal using the empirical error, which is written as R S of H, which is just can be understood as exactly the same as loss or the error that I just told you, but uses empirical distribution instead of the real target distribution. Or you can think of it as just sample average. So we have taken average, the sample I is equal to 1 to m plus of h of xi and y. So the algorithms, most of any algorithm that you're gonna think about, we will discuss, it will exploit this information, the information that's in this empirical loss. And or it will compute empirical loss, the empirical loss by empirical error, and then maybe it will do a bit more, like it will also consider complexity of each hypothesis. But in doing so, it will try to find H that minimize our ultimate goal, which is R of H. And as I said, just to emphasize again, I told you the loss is defined typically by using this structure, metric structure of the space, output space. So, and then it's softer than in the sense that it's not like a 0 and 1. It gives some gradual feedback to the hypothesis. So that's the one. What makes all the difference in the regression part. Now let me mention one more thing. Okay. Now suppose, okay, I said here, let's think about this LP to have some understanding about the impact of the choice of this loss function. And then now if we draw this function LP, here's my very likely better drawing. Sorry. Think about LP prime. This is defined first taking the difference and then taking the power. P is greater than equal to 1. So now, what's the impact of choosing different P? Now, if we draw this picture, so not this loss, but some functions which maps x to the power of P, then if P is equal to 1, we get the line. It's just the absolute value, so we get line here. It's equal to, P is equal to 1. Now, if P is squared, then it will be some values smaller than 1. it will decay slower than the, the absolute value function, but value for larger than 1, it will become grows faster. So this is x squared. So then maybe if we take x cubed, that will have a more extreme behavior, like x cubed. It's even slower, difficult. So like this, it's a very bad picture drawing, but it was like this. So what does that tell us? That tells us that if we increase, this means that if we increase p, so then these things happens, like a large deviation, which happens in this regime, like in this regime and in this regime. The large deviations gets penalized more because you will get high loss, but small deviations get penalized less. So that's what's happening in this region, like this. Okay, so if we have a problem where we really want the hypothesis that we learned does not really deviate that much from the real target, then maybe using the larger p is a good idea. But if, on the other hand, what we want is that we know that our algorithm is able to achieve very low error, and then we want this. So we are in this red regime, but we want the error to be very, very small. So then maybe using p is equal to 1 is a bit better idea. So that this different choice of p will, in a sense, provide different guiding principles about what kind of thing we want to achieve using a regression algorithm. Okay. Right. So that's the regression problem. And before actually talking about the regression problem, let's discuss some theories about the regression problem. And this general theory will be used again and again when we analyze the algorithms that I'm going to explain to you later. So learning theory. For bounded regression problem. So here, bounded means, now we said the loss functions is just, it's take 2i's and then return 0 and infinity. So that was our loss function. But in the bounded case, actually, so this is unbounded case and not unbounded general case. But the bounded case is the one where the target of the loss is bounded by some constant m. So I think I'm sure there is some theory which people developed to deal with this general case, but I think the theory is substantially more difficult than what I'm gonna tell you now. So I think the textbook, the authors make a decision that they're gonna only present the theory for the bounded case. So this theory may be not applicable in all the problems that you will encounter, maybe very limited, but it will still provide some guiding principle to analyze or understand algorithms algorithms and problem. Okay, so what kind of things we can do in this learning theory, and then let's study something very simple first. We study two things. Textbook presents three things. One is based on finite case. Our hypothesis set is finite. And the second is for the generalization. Potentially infinite, but it's bound obtained using the Rademacher complexity. And the third is something called the pseudo dimension. And the last bit, the pseudo dimension thing, I found very confusing. I'm not entirely sure whether the story there is consistent. Sometimes it seems that they are using one definition. Sometimes they are using different definition. That may be because I didn't quite understand what they tried to say. So I decided, I'm not going to talk about that part and focus mostly on the first two parts. First is more like a warm-up. So we consider first case, it's called finite. Our hypothesis set is finite. So throughout the entire section, we make this assumption. Okay, our loss function is bounded by some large m. Okay. So then the first case is that we have a hypothesis which is finite, and in that case, can we say? Question is, can you have a uniform generalization bound? So the answer is yes. It's actually quite easy. Then it's very similar to what we looked at when we discuss about PEC and the inconsistent case of PEC. In the learning chapter. So what does that mean? That means that essentially we can derive a bound on the uniform generalization bound in this case by using the two ideas. It's a union bound and Hofstad's inequality. So here are the results. The results say the following. Here, 11.1. It says that so we are making the assumptions on the bounded assumption always in this section, and this is for the finite case. So suppose H is finite, and then consider some distribution for the problem, and the level of accuracy we want to achieve the size of sample. That's the case, and the following bound is true. Probability that for H, our risk that the real or generalization error defined in terms of a loss L is bounded by empirical loss or empirical error is bounded above is going to have a high probability if we put some extra term. That extra term has is m square root of log of h, size of h plus 1 over delta. It happens with high probability. So with high probability, there's a risk, generalization error, loss will be bounded by empirical loss plus some extra term that depends on the bounds on the loss function. So this m plays a role here. And then the rest looks very similar to the one that you saw when we discussed about the generalization bound for the inconsistent case. So I don't know how many of you actually remember the proof, but it's good to try prove this for you. That may help you to remember what you studied before. And proof is actually quite simple. So try to prove this. I will give you maybe 3 minutes to prove this theorem. And then through the proof, in the inconsistent case for classifications, this m was equal to 1. So instead of having 1, m, we had a 1 there. And then think about why we have 1 in one case and then m in the other case. Okay, so let me tell you how to prove this. As I said, it's not very difficult. It's just using union bound and Hopkins inequality. So let's put epsilon to be m square root 10 log. Log, we just combine this log of h and log of 1 over delta. That is same as h, size of h divided by delta. So let epsilon like this. Then what we have to prove? We have to prove the probability that exists h. We have to show that there exists a violation of this property, which is r of h minus r hat of h is greater than epsilon, is small. So less than equal to that. That's what we have to show. So then the question is how we can show this. So we will do some manipulation here. So we'll keep finding something larger than this probability and eventually show that that's smaller than equal to delta. Now, the first thing is a union bounds. We look at this existential quantification here. H, because H is finite, and some H have this property is probability of some H have this property is bounded above by sum of this probability R of H minus R hat sub H greater than epsilon. So this is coming from the union bound. Then we unpack the definition of, this more in the style where it's a bit more obvious how to use Hopkins inequality. And then, so we just massage in this term and convert it in the equivalent term. H probability. Say the R head of S is in sum. It can be written like this. So M loss of H of Xi. Then the other ones can be seen as expectation of this sum. H of loss of H of Xi Yi, where the expectation is over all these Xi. Then what it says is that I think that's smaller than minus m epsilon. So from the R of H by multiplying R of H with M, and then you just kind of unpack the definition and do a little bit of calculation. That's same as this. If you compute minus M R of H, that's same as this term here with minus. Then for if you multiply minus M to this minus R head of S, that will become same as this guy. And then for epsilon, we multiply minus M, and because we multiply negative number, the symbol is greater than becomes less than. So now once we have this form, this is exactly the form where we can apply Hopkins inequality. Hopkins inequality said if we have this M independent random variable, sum of M independent random variable minus their expectations it deviates quite a bit from the expectation. So this becomes quite small by being smaller than minus m epsilon. Then that probability is bounded by this Hopkins inequality. And then that Hopkins inequality said it's an exponentiation of minus 2 times this minus m epsilon square divided by, for each of the random variable, which is L of H, Xi, Yi, we measure their possible, the size of their range, and then square it and sum all of them. So for every such case, we have I is equal to 1 to m. The L can have a value between 0 and m. So if we square measure their range, size of their range, and the square them is going to be m squared. Then it goes like this. Now, if I plug in epsilon here, do a little bit of calculation, that is exactly the same as delta. So I mean, I'm not going to do it, but if you plug in epsilon here and do calculation, you get exactly that. That's how you prove it. So the key idea is, as I said, the using the union bound and Hofstad's inequality. And then I ask where this M actually comes from. And then this M comes from the fact that this, just use a different color. I said where M this come from. This M come from the fact that the L has the range, its range is between 0 and M. So that's why we have an M here in the bound. In the case of classification, we are using the indicator function. So its range is, I mean, either its output is either 0 or 1. So that's why we have 1 instead of an M in that case. Okay. Right. So that's the generalization bound. And what's the message of this generalization bound? The message is that if H is finite, then I mean it's not sufficient to minimize the empirical error. Okay, it's also good to pay some attention about how to manage the complexity of the hypothesis set. So if you use a smaller hypothesis set to achieve the same thing, that is much better because you will have a tighter generalization bound there. So it's the same principle. So the principle that we studied, which is sometimes called Occam's razor, for some problem, choose the simplest descriptions, was choose the simplest hypothesis. That is also equal, a good, in a sense, heuristic. That's in the context of the regression. Okay, so but what we studied this for finite case doesn't really work most of the time because hypothesis set is typically infinite. So what should we do for the infinite case? So in that case, we have to use the Rademacher complexity. Complexity bound. So here's one lemma that I perhaps write it first, and then we'll prove the theorem later. So the one key lemma is that we have something like proposition 11.2. This is something very similar to the, essentially the application of Talleyrand lemma. So what this lemma say is that it allowed us to compare the Rademacher complexity of two different hypothesis sets. So suppose we have sample S. So the scenario is the very same. We have L that's described as before, but we assume one more. Say that L that exists, mu, such that L blank Y, which is going to be a map from Y to 0M, is mu Lipschitz. So what does this mean? This means that for Y0 and Y1, the difference between L, if you plug in two different inputs, it's going to be bounded by 0. So that's what the definition of Lipschitz continuity tells us. This happens for all Y0 and Y1. But more useful property is, this is when the L, this partially applied function L is differentiable with respect to first parameter. So mu Lipschitz is same as the gradients or the derivative of L with respect to first parameter is bounded by U. So say the same thing as you take the derivative, and if it's compute its absolute value, that's going to be bounded by U. So in a sense, the slope is bounded by U. And so that's what Lipschitz continuity tells us. And then we consider, we have a hypothesis H, but we consider new hypothesis G. That's consists of function that take x and y and returns x, y, where H is our hypothesis. So then what this lemma tells us is that it tells us the relationship between Rademacher complexity of G, empirical Rademacher complexity of G, and empirical Rademacher complexity of H. So that's what the Talagrand lemma say. And why we care about this? We care about this because the basic result that we proved long ago about Rademacher complexity is mostly about G. Okay, it's mainly about G, but the Rademacher complexity we are more interested in is not the Rademacher complexity of G. We are interested in Rademacher complexity of H. So we want to rephrase the general result, which is expressed in terms of G, in terms of H. Okay, an expression that uses H, and the Talagrand lemma allows us to do so. And then the key is that using this view Lipschitz property. And so that's the conclusion is that empirical Rademacher complexity of G is bounded above by U times empirical Rademacher complexity of H. But when we compute the empirical Rademacher complexity of H, we are only looking at the X components of S. So this is same as this one. So I didn't really write. So we have another thing, which is S is the sequence of example. And that's the so it allows us to connect the empirical Rademacher complexity derived from the composition of H and loss and the empirical Rademacher complexity of our hypothesis. And then the proof is a direct application of Talagrand lemma. So the reason I'm hesitant is because it looks like I'm just telling you the Talagrand lemma and then say, oh, it's a direct application. So it doesn't feel like it will carry any information to you. So let's just take 11.2 as it is. So we have yes, mu is universally quantified for all. Okay. So for all y, this is the case. And thank you very much. Put it like this. So it's like a uniform Lipschitz condition. Okay. So then let's use this to prove the next main theorem. So from here, there's something that you perhaps need to remember is that we have a H and G. If our loss is a mu Lipschitz, then the Rademacher complexity of G, which is really computing the composition of hypothesis and loss, is related by this having this relationship with Rademacher complexity of H. Okay. So let's use this to prove our main theorem. So the main theorem is this one, which will be used many times. Theorem 11.3, 11. So this theorem says the following. We have the loss function L, and then so there, I mean, just the conditions that we talked about, they're all true. So just write all the condition here. So loss function, but it's bounded by M, and also there exists mu such that for y, partially applied y is mu dipshit. So what we discussed before applies here. Then the typical quantifications, which is the problem, and the part precisions, and M. Then the theorem say two properties are true. So the theorem talk about two uniform bound. The first uniform bound say the following. For M samples, then we can say for H in our hypothesis set, its error with respect to the loss that we talk about is bounded above by it's an empirical loss or empirical error plus 2 mu R of H. So Rademacher complexity with M samples plus square root of M times 2 log 1 over delta. And that happens with high probability. So the general results that we studied when we looked at the classification looks very, very similar, except that it doesn't have M. So in that case, loss is like this indicator-based loss. So M is equal to 1 in that case. And also this 2 mu is just equal to 1. So there's just some difference, and then those differences are really coming from we are having more sophisticated L, which have some structure like, it's bounded by M, and then mu Lipschitz continuous. There are just other versions which instead of using the Rademacher complexity uses empirical Rademacher complexity. So that version say instead of the 2 mu R M of H, that version talk about using R of empirical Rademacher complexity of H with respect to X. And then this part also change as usual. So we have a 3M square root of 2M log 2 over delta. These changes are essentially the same changes that we got when we studied this bound in the context of classification. So now the question is how we can prove this. So in the context of a classification, we looked at something very, very similar. Okay. And but there's just some difference. So in the context of classification, actually we proved something quite general. What we proved is that we said, okay, we have a maybe just write it and then so classification we said if we have a function class f, it's just a mapping from inputs, which is typically x times y. Just write it here. Okay, let me explain that is why we the previous theorems by proving this theorem. So let's define. So what we're gonna do is we'll use theorem 3.3 and then the proposition 11.2. And also, strictly speaking, we have to use Talagrand lemma again. That's how we can prove this theorem. So how to do it? We first define G prime, which is very much like a G that we talked about, but there's just some slight difference. right? It maps xy to loss of h of x, comma y, where h is an h. So far, it's the same as the definition of g, but we normalize it by 1 over m. Okay. So if we do so, then every function in g primes is because the small g, okay, so small, I mean, because the loss functions is the range of the loss functions is 0 and m. If we divide by 1 over m, the range will become 0 and 1. Okay, so just divide 0 and m by 1 over m by m, then you will get the range will become 0 and 1. So then we have a collection of functions, or measurable functions, and then which from some input space, like x comma y, to output, which is 0 and 1. So that's the context where we can apply theorem 3.3. Okay. So theorem 3.3 tells us that we can, the following is true. So what theorem 3.3 say is that, I mean, it allows us to have a uniform upper bound of some quantity by its empirical estimates. Okay. So that as long as the functions that we are dealing with is bounded, that its range is between 0 and 1. Okay. The output is between 0 and 1. So by theorem 3.3, we have this property of m for g prime in g. If we compute this expectation of one L, compute expectation of this guy with respect to the distribution. So it's really, theorem 3.3 really say, I mean, how we can have a uniform bound on the expectation. Then we have another term, that another term is empirical estimate based on the examples in the sample. So this empirical estimate is like this. So m g prime of xi, yi. And then we said this happens with high probability, the probability 1 over delta. But to say this, we need to put some extra terms. That term comes from Rademacher complexity, 2 times Rademacher complexity of the hypothesis at g prime plus 1 over square root, square root of, this thing, 1 over delta. So theorem 3.3 just say that expectation is bounded by its empirical estimate with high probability, as long as we put this extra term, that's a 2 times Rademacher complexity plus some other term coming from essentially Hopkins inequality. Okay, so then now we have an expression in terms of g prime, but we know that every g prime is of this form. So every g prime is essentially g divided by 1 over n. Okay, so this side becomes the same as g. Now, every g prime is 1 over m times g. So if you plug in 1 over m there and 1 over m for every place where we have a g prime, and then we multiply this capital M everywhere, then we get this quantum expectation of xy d of x comma y. M of xi yi. Because we multiplied m everywhere, we have 2m m prime and m of square root of 2m log 1 over delta. So we have this probability is still large, but it's greater than 1 over delta. Now, how can we complete the proof? One way to complete the proof, so we just keep unpacking the definition. So what is G? G's are always, it maps x comma y to the loss of h of x comma y. So this universal quantification can also be written like this. For h, expectation of x comma y, where L of hx comma y by m summation of I is equal to 1 to m, and this is L of h of xi yi plus 2m r of m g prime is m square root of 2m log 1 over delta. So what should we do to complete the proof? We are almost there. If you just do the pattern match, for the first statement, and then what we derived here, this happens with high probability. The only difference between the two lies in this term. So because we are doing upper bound, if we can show that in mu of Rm of h is greater than Rm m of Rm of g prime, then we are done. Okay, so this is what we have to prove. Now, how can we show this? So now we compare G prime and G. And then actually, one thing you can say is that G is obtained by essentially just dividing everything in G prime by multiplying 1 over m. So this multiplying 1 over m is really a mapping that takes value y, not really y. Mapping that makes take a and divide, return 1 over m of a. This is 1 over m Lipschitz. So if we have a two hypothesis set and one hypothesis set obtained by another hypothesis set by composing some Lipschitz function, Talagrand lemma said there's a relationship between Rademacher complexity, which say the Rademacher complexity of G prime is upper bounded by the Lipschitz constant and the Rademacher complexity of G. This is Talagrand lemma. And now about proposition 11.2, which is essentially say the same thing. We have we try to compare Rademacher complexity of this Rm and then Rademacher complexity of Rademacher complexity of G and Rademacher complexity of H, and this, the proposition say that is actually related by mu times Rademacher complexity of H. That's because essentially, if you can obtain one function, the hypothesis set from one set of functions from the other by composing some mu Lipschitz continuous functions, there is a corresponding relationship between Rademacher complexity. So we can prove this, and then that's coming from proposition 11.2. And that's exactly what we have to show. That if you move m to the other side, then that corresponds to this is statement that we want to prove. And we just proved that statement. Right. So this gives the complete proof. And then although it looks complicated, I mean, this formula is not so bad. I mean, we're gonna use it multiple times to analyze the algorithms maybe on the Thursday, not on Thursday perhaps, but the next week and a week later. Okay, so I think I have about 3 more minutes, but instead of moving to the next topic, maybe it's better to stop here. So I'm gonna stay here for about 5 more minutes. So if you have any question, you can ask me. Okay, so thank you very much.